Hello everyone. Did you ever wonder what happens when a tiny charged particle dances through a magnetic field? Well, it turns out that this little dancer feels a special push called the Lorentz force. Here's a fun physics joke for you. Why don't magnetic fields ever get lost? Because they always know their direction. Now, let's break down this magnetic mystery. Imagine a charged particle, say an electron or a proton, moving with some velocity, which we'll call vector v. When this particle enters a magnetic field, represented by vector b, it experiences a force. And this force isn't just any force, it's given by the vector equation F equals q times the cross product of v and b, where q is the charge of the particle. To picture this, imagine vector v as the thumb of your right hand, vector b as your fingers extended, and the resulting force F comes straight out from your palm. That's the famous right-hand rule, which only works if the charge is positive. Negative charges just get the opposite direction. Now, the size or magnitude of this force depends on how fast the particle is moving, the strength of the magnetic field, and the angle between the velocity and the field. Mathematically, it is given by the force F equals charge q times velocity v times magnetic field b times sine of theta, where theta is the angle between v and b. When the velocity and magnetic field are perpendicular, that is, theta is 90 degrees, the force is at its maximum. In fact, this force makes the charged particle move in a circle, acting as the centripetal force that keeps it turning instead of flying off in a straight line. And here's a cool fact: the unit of the magnetic field, called the Tesla, is defined based on this force relationship. 1 Tesla is the magnetic field that exerts 1 Newton of force on a 1-coulomb charge moving at 1 meter per second. Now, moving on from a single charged particle to a whole conductor carrying current, think of a wire packed with moving electrons, all zipping along together. The magnetic force on this wire is basically the sum of all those tiny Lorentz forces acting on each moving charge. The total force, denoted as vector F, is given by current I times the cross product of vector L and vector B. Here, current I is the total flow of charge, vector L is a vector representing the length and direction of the wire segment, and vector B is the magnetic field vector. Just as before, the direction of this force is found using the right-hand rule. Point your thumb along the current direction, your fingers along the magnetic field, and your palm points where the force acts. That's an easy way to predict what way the wire will push or pull. The force reaches its maximum when the conductor is perfectly perpendicular to the magnetic field, meaning theta, the angle between L and B, is 90 degrees and is 0 when the wire runs parallel to the field. In numbers, we write the force magnitude as F equals I times L times B times sine theta. And this principle isn't just theory, it's the secret behind devices like electric motors. The magnetic forces create torque, a twisting force that turns the motor's shaft, powering countless machines around us, from your electric fan to massive industrial tools. Picture in your mind a straight conductor placed inside a magnetic field, with arrows showing current moving along the wire, the magnetic field lines crossing it, and a force vector pushing perpendicularly. You can almost feel the push. Let's see how we know this is true. The proof is always in the pudding, or here, in the experiment. Imagine a straight wire hanging in a uniform magnetic field. When you pass current through this wire, you'll observe a sideways push or deflection, proving that the magnetic force is real and measurable. The magnitude of this force depends on 3 factors: the length of the wire inside the field, the current flowing through it, and the angle between the wire and the magnetic field. The formula is the same trusty friend: force equals current times length times magnetic field strength times sine of theta. And here's something neat: if you reverse the current direction or flip the magnetic field, the force swings the other way, exactly as predicted by the right-hand rule. This reversibility is a great confirmation of the magnetic force's direction. The deflection you see in the wire's position isn't just a movement, it's direct evidence for the magnetic force acting on currents. Historically, this experiment was a key step for André Ampere to understand how electric currents interact with magnetic fields, laying foundations for electromagnetism. Think of the diagram as a simple setup, a wire suspended between poles of a magnet, with arrows showing magnetic field lines crossing the wire, the current indicated along it, and a visible deflection showing the force direction. Understanding the direction of magnetic force is crucial, and it all comes down to vector cross products. Yes, that fancy math deserves a friendly explanation. The force vector F equals current I times the cross product of length vector L and magnetic field vector B. To apply the right-hand rule correctly, point your fingers in the direction of the wire, that's our vector L. Then curl them toward the magnetic field vector B. The direction your palm faces is the force acting on the wire. Easy once you get the hang of it. But what if the wire runs exactly parallel to the magnetic field? Then the angle theta between L and B is 0, sin theta is 0, and so the force is 0. No push, no pull, the magnetic field and current are in harmony, no force acts sideways. Keep in mind, you have to be careful about current sign and magnetic field orientation, otherwise, your force direction prediction might get flipped. This knowledge is the backbone of how coils twist and motors spin. When the current-carrying loop feels torque, it's this force direction playing its part, causing rotation around an axis. Picture a three-dimensional set of axes with vector arrows for L, B, and F, showing clearly how the direction of force comes from their cross product. This picture is like physics magic in action. Time to crunch some numbers and see theory become practice. Suppose we have a wire segment carrying a current of 5 amperes with length 0.3 meters placed in a magnetic field of strength 0.4 Tesla. The angle between the wire and magnetic field is 90 degrees, that's perpendicular, so force should be maximal. Using the formula force equals current times length times magnetic field times sine of theta, we substitute 5 amperes times 0.3 meters times 0.4 Tesla times sine 90 degrees. Since sine of 90 degrees is 1, this simplifies to 5 times 0.3 times 0.4, which equals 0.6 newtons. So the magnetic force on this wire segment is 0.6 newtons, and this force acts perpendicular to both the current direction and the magnetic field direction. If you check the units, amperes times meters times Tesla gives us newtons exactly, confirming our calculation is dimensionally consistent. For such everyday lab values, 0.6 newtons is a sensible force, enough to produce noticeable movement in sensitive setups. Imagine the diagram, a wire in a magnetic field with clear arrows marking current flow, magnetic field lines, and the force vector pushing at right angles to both. Let's wrap it all up. At the heart of magnetic forces is the Lorentz Force Law. The force on a single charge equals charge q times the cross product of velocity vector v and magnetic field vector b. Scaling up from charges to actual currents in a wire, the force on a current-carrying conductor equals current I times the cross product of length vector L and magnetic field vector b. The magnitude of this force is current times length times magnetic field times sine of the angle between the conductor and the field. The direction of this force isn't mysterious, it follows the right-hand rule consistently and reliably. This force arises because magnetic fields push on moving charges inside the wire, and their combined effect pushes the whole wire. This magnetic force causes real-world effects like the swinging wire in experiments or the spinning rotor in electric motors. So, this isn't just textbook stuff. It's the physics making your fans spin and your electric trains run. That is it for today's concept. Remember, physics is much more fun when you can laugh and learn at the same time. See you in the next session.